we were introduced to parts per million and parts per billion in a previous video on other ways of measuring solution concentration. That video was pretty long, so I wanted to break out the ppm and ppb examples into a separate video. Alright, so our first example. The EPA has set the maximum contaminant level of uranium in drinking water at 30 parts per billion. And so I've got a 500 gram sample of drinking water, and it contains 1.89 times 10 to the minus 7 moles of uranium, and I want to know, is it above the MCL, the maximum contaminant level? And we're also told we can assume the density of solution is 1 gram per milliliter. Just as sort of an aside, when we're dealing with parts per million and parts per billion, we're typically talking about really low concentrations. And so it's very often, even though they don't tell us in a specific example, or you're doing a problem not in this chemistry class, it's often an okay assumption to assume that the density of the solution is the same as the density of water, because it is such a low concentration. Alright, so in thinking about this problem, let's write down the formula for parts per billion. So parts per billion is the mass of the solute divided by an SOL apostrophe N. That's a common abbreviation that people use for solution because chemists are lazy and we like to find shortcuts. And then the multiplication factor is 10 to the 9th. And so I want to compare the concentration of this solution in parts per billion to the MCL. So I need to calculate the concentration in parts per billion. So I need the mass of the solute and I need the mass of the solution. The mass of the solution is easy. They just gave that to me. That was the 500 grams. So in order to solve this, I need to find the mass of the solute. Well, they gave me the moles, and so I know I can get mass from moles by using the molar mass. And so we just have an element, so I can just get the molar mass from the periodic table, 238.03. And so my moles of uranium, or the solute, is times the molar mass and so I have 4.50 times 10 to the minus 5 grams of solute. So then to find the parts per billion, I would just take that mass of solute and so my concentration comes out to be 90 parts per billion. So the answer to the question is, does it exceed the maximum contaminant level? The maximum contaminant level is 30 parts per billion. We've got 90 parts per billion, so yes, this does exceed the maximum contaminant level of uranium in drinking water. Alright, I have a second example here. So the hardness of water is usually expressed in parts per million of calcium carbonate, in parts per million by mass. And I want to know, what is the molar concentration of calcium ions in a water sample with a concentration of 225 ppm of calcium carbonate. And again, we're going to assume that the density of the solution is the same as that of water, 1 gram per milliliter. So this problem is going to be a little bit more involved than the last one, and I'm going from one concentration unit to another. And so whenever I have these more complicated problems and I'm going from one concentration to another, I'd like to use Mike's table. So let's make Mike's table. Alright, now at first glance, it seems like maybe we don't have enough information. Like, all we're given is the concentration in ppm. Whenever you're working these concentration problems and they don't tell us the amount of solution we have, we can go ahead and assume however much we want. And so we can make it hard. We could assume we have 1.26 times 10 to the minus 5 grams of solution, but that's going to make it hard, right? It'll be much easier to assume a convenient amount of solution. And so let's assume that we have 100 grams. If that's the case, because the density of the solution is 1, we also have 100 milliliters. Now, if we think about the problem, we're looking for molarity, right? Molarity is the moles of solute divided by the volume of the solution. So we need the moles of solute and the volume of solution. And we have the volume of the solution. So we need to see how can we get the moles of the solute. Well, the equation for parts per million is the mass of the solute divided by the mass of the solution times 10 to the 6th. And we have the concentration in ppm, that's the 225. We have the mass of the solution, that's our 100 grams. So the only thing we don't have here is the mass of the solute. So I should be able to use the ppm equation to find the mass of the solute. That'll give me this, right? And then I know I can go from mass to moles using molar mass. That'll give me the moles of the solute, and so then I have everything I need to get the molarity. So let's fill in everything we have for the ppm, and we're going to solve for the mass of the solute. I'll call that x. So the ppm is 225. We're looking for the mass of the solute. We have 100 grams of solution times 10 to the 6th. So the first thing I'll do, let's get rid of this 10 to the 6th. Multiply both sides by 100. So the mass of the solute is 0.0225 grams. Okay, so then to find moles of the solute, I need its molar mass. I need the molar mass of calcium carbonate. So I've got 1 calcium, 1 carbon, 3 oxygens, and so I get a molar mass of 100.09 grams per mole. So I'll take my mass of calcium carbonate, divide that by the molar mass, nope, I'm sorry, it should be 2.25 times 10 to the minus 4 moles. So I have 2.25 times 10 to the minus 4 moles. And then the last thing I need to do, now I know the moles, right? I know the volume in milliliters, so I need to be sure I convert that into liters. But then I have everything I need to calculate the molarity. So V is 100 milliliters. And again, I'm just going to do this in my head. You want to be able to get to the point where you can go from milliliters to liters in your head. We just need to divide this by 1,000. So we have 0.1 liters. So then the molarity take the moles of the solute, divide that by the volume of solution in liters, and we get 2.25 times 10 to the minus 3. Now, just a word of caution. If you'll notice, the concentration of ppm was 225, and then we get 2.25 times 10 to the minus 3, and so it kind of looks like, maybe there's an easier way to get between parts per million and molarity. But the reason that numerically they're so similar is just a function of the fact that the molar mass of calcium carbonate is about 100. And so, if this had been any other compound, then there'd be no numerical similarity between the ppm and the molarity. That's just an artifact of the fact that this particular compound has a molar mass of about 100.